Morning, Year 11s. Sorry I couldn't come in today. I really wanted to be going through your exams with you, but that's just going to have to wait till next week. I'll have your percentages on today so that you can look at them. But I wanted to get started on the next semester, and rather than you just read the chapter, I thought I'd talk to you about it while I can. So we spent first semester looking at ionic bonds and covalent bonds and metallic bonds, and looking at all of the way that the atoms are held together, so the intramolecular forces. And that's, you know, the forces that are actually holding the molecules or the lattices together, the forces between the atoms. Now, this semester, we are moving on to intermolecular forces. So that's the things that hold the molecules together. Why is water a liquid at room temperature and nitrogen's a gas? Why don't the water molecules, because they have the same number of protons, the same number of electrons, why don't they all just float away from each other? What is the thing that's holding them together? And water is going to be a really big focus. There's a whole topic on it, and there's an assignment on it. And I'll give you that question really early so that you can start researching it. It's going to come up about week 3, I think, next term. So intermolecular forces are the things that are holding the molecules together. And the first thing that we need to look at, or one of the main things that causes the molecules to stay together, is their shape. So I've got this, this is methane, CH4, and the most important thing that you need to understand is that the electron pairs are going to move as far away from each other as they possibly can. So you're going to end up with this tetrahedral shape of your molecule, which is quite symmetrical, and the electron pairs are going to be as far away from each other as they possibly can. If you've done any kind of 3D vectors in maths, I know some of you might be doing some of that. You'll probably be able to use maths to figure out the maximum distance. We're not actually going to do that here. The maximum distance between these in a sphere is going to be 109.5 degrees. Now, you don't need to know the number. What you really need to understand is that the electron pairs are going to move as far away from each other as they possibly can. So, and it's called the VSEPR model, valence shell electron pair repulsion. I'll just put something up for you to write down. That's your first important thing, is that to understand that the electron pairs are going to move away from each other, as far away from each other as they possibly can. This is not the best way to do it. So just write that down, this thing about the VSEPR theory. Electron pairs will always move as far away from each other as they possibly can. So that's valence shell electron pair repulsion. I can't write now, I've got a new page. Okay, so valence shell electron pair repulsion, which just says that those electrons are going to move as far away from each other as they possibly can in a molecule. So here's your CH4. And it's got 4 hydrogens in that, and the hydrogens are bonded to the carbon electrons, and they've moved as far away from each other as they can. Now, I'm going to take one off, and this is going to be NH3. So nitrogen, 3 hydrogens. There's still a lone pair of electrons up here. So they're still going to come into this shape that's a pyramid. And they're actually going to be a tiny little bit closer to each other because this lone pair of electrons is pulling more strongly towards the carbon atom, the nitrogen atom. So I'll show you that. So nitrogen is element number 7. So it's got 2 electrons here, and it's got 5 out here. 1, 2, 3, 4, 5. Remember, that's 3D. So they're pulling away from each other as much as they can. and get a hydrogen come in here and give it an electron, get a hydrogen come over here and give an electron, and a hydrogen over here giving an electron. So you've got three hydrogens and a spare electron pair over here. So you end up with a shape that's kind of like that. I think we'll just move to the next one. We'll talk about what that means, bonding. So this one's going to be water. Okay, there's still two spare electron pairs, and I'll show you again. There's oxygen. Oh, there's the first shell, 2 electrons. Oxygen's number 8, so it's got 6 electrons out here. 1, 2, 3, 4, 5, 6, and you've got your hydrogen there and your hydrogen there. And because those other 2 pairs of electrons are still there, they're still repelling each other, the water molecule ends up in this bent shape like that. Now, if you have a look on your, hang on, I'll just find a table. There's a table on page 270, but I can put something similar up here. Where did it go? Hang on. All right, so this interactive periodic table is really cool. Oh, and I've put it on sector so you can have a play with it. Now, if I change the temperature, it tells you which elements are solid, liquid, and gas at a certain temperature. So the ones that are in black are solid. The blue one here, gallium, that's going to be a liquid at that temperature, and it tells you what temperature we're at, 36 degrees. And chlorine is going to be a gas. And if I change the temperature, it tells you which elements have changed from a solid to a liquid to a gas. Now, down the side here, you've got all of these bits of information. So this is rubidium, and it tells you its weight and its electronegativity and its melting point and its boiling point. And I can click on molybdenum, and it tells me everything about molybdenum. You can also, across the top here, you can have a look at how the electrons form around the shells. Now, this stuff is probably next year's chemistry, so you don't worry too much about that. It can tell you all the isotopes. I can go, look, carbon has all of those isotopes, tells you their relative abundance, and it just pops up in this table down the side. Compounds. Here we go, water. And there it is, H2O, ice, steam, water. So what I really wanted to show you though was that there's this electronegativity table, and it's also in your textbook. And just looking at this water molecule, you've got hydrogen with an electronegativity of 2.2, 2.2, and oxygen's more electronegative. So you're going to find that the electrons are hanging out more around the oxygen than they are around the hydrogens. So because this is not a symmetrical shape, because the shape is not symmetrical, you're going to have a more negative end here and a more positive end over here. And it ends up being, it's called polar, where you've got more negatives at one end and more positives at the other end. And they kind of join with other water molecules. They're attracted to other water molecules, but not quite the way ionic bonds form. They're not the differences, the strength of the attraction is not as strong, but they're still attracted to each other because one end is more negative than the other end, so it'll end up making this kind of joining like that, which is why we have liquid water. But back to the whiteboard. All right, put that off, and now I've got hydrogen fluoride. So just put that one here, hydrogen fluoride. This one's just going to be a bit easier to show you what's going on. And hydrogen fluoride is like a straight line, right? Because that's all. There's still electron pairs around here, but the molecule itself is linear. Now, fluorine has an electronegativity of 3.98. And hydrogen has an electronegativity of 2.2. So you end up with this overall more negative end and a more positive end. We write this with this Greek delta. This is a lowercase delta, not like your triangle, you know, with your delta H was a triangle. That's capital delta. This is lowercase delta. Okay, so this end is a bit more positive, and this end is a little bit more negative. And how much more negative? Well, it's 3.98 take away 2.2. It's the difference. So we got a 1.78. 1.78 what other units? I'll have to look that up. There's 1.78 units, you know, more electronegative at the fluorine end than at the hydrogen end. So another hydrogen fluoride is going to come along and it's going to align itself. The hydrogen is going to want to join in that end because hydrogen's a little bit positive, and the fluorine's going to want to get over there and find another hydrogen and another fluorine. So the reason that the way that these molecules attract each other for a lot of them is that one end is more positive and the other end is more negative. So it's a little bit like an ionic charge, but it's not quite as strong. And the strength of the charge comes from the difference between the more positive end and the more negative end. Now, there's also an interactive that I want to see if I can drag up and show you. Hold on. All right, so this here, just, I don't know how useful it is, but I saw it and thought it might help a little bit. So if atom A is less electronegative and atom B is more electronegative, like hydrogen or fluoride, you're going to get more electronegativity down this end. We can't put numbers in there, so we can't actually see real molecules. There's this here that says 3 atoms, and let's see, if A is electronegative and C is very electronegative and A is less, and C is less and B is more, then you're going to get more negative pull in that direction. Now, if we increase C, the electronegativity, the charge, the pull on the electron is going to be in, the negative charge is going to be more in that direction. And then, you know, it gets smaller and it goes more in that direction. So I don't know, you can have to play around with that. It's on your sector as well. Now, oh, there you go. You've got the individual strengths of those charges and the direction of those charges. I'm going to go back to 2 atoms because I think it's a bit easier to look at. And also, you can see that if you've got one that is completely negative and one that is completely positive, you've got an ionic bond. But ionic bonds and covalent bonds, there's a kind of in between there somewhere. So the more similar they are, the more covalent they are. The more similar they are in electronegativity, the more covalent they are, which is why you've got all the nonmetals down one end of the periodic table with covalent bonds, but you've got those opposites at opposite ends, the metals and the nonmetals having ionic bonds. So you can play around with that and see if that helps you to understand it. And then there's the whiteboard again. And I'm going to just put up a couple more notes for you. I won't cut and paste, I'll just put this straight up here. The VSEPR theory, which is what I got before. You've got molecule kits so that you can make those things so that you can see the angles between the molecules. And then I've written this bit, polar and non-polar molecules, so that you can, so you can write that down. Polar molecules are asymmetrical, so which means they're kind of like that and they're not that nice, neat tetrahedron. The atoms have got varying electronegativities, so the electrical charge is not evenly distributed. There's a more positive part and a more negative part. Polar molecules are attracted by dipole-dipole forces. So, and the partial charges are represented by the Greek letter delta, and there's a picture of that there too. So, I'm not sure what I'm doing now. Right, so molecules that have got a more positive and a more negative end, or that are not symmetrical, are going to be polar, and they have a more negative and a more positive part, so that they're attracted to each other. It's kind of like an ionic bond where you've got a negative and a positive being attracted to each other, but the attraction is not quite as strong. Right, so have a look through the chapter, through the start of chapter 12, the first section, maybe even 12.2, and have a go at answering some questions, have a play with the molecule kits, have a look at that interactive periodic table. It's got some really good uses that's going to be really useful to us, I think, in second semester. And have fun. I'll see you Monday.